Okay, so cardio-phys video question 1, we're going to talk about conduction, we're going to talk about depolarization, and heart failure within the heart, obviously. So the heart is made up by heart muscle, which is made up of individual cells, as we see here. Within each cell, there is this lighter blue part you see is called the myosin, and then this purple part is the actin. And the whole purpose of actin and myosin is to kind of act as little ratchets that will cause the muscle to shrink and contract. It'll pull itself into each other, and it'll cause the muscle to contract and exert force. And the way that this happens is we have calcium running down a signaling channel that will essentially talk to like these voltage gated channels within the heart and cause binding of calcium at this streptomyosin, and this activation will initiate that contraction and that shrink that we were talking about. So whenever we have a line of multiple of these muscle cells, as they all grab to each other and contract and shrink, they will cause a contraction of the entire muscle. Within the heart, what that ends up looking like is, if this is like the ventricle, we would see contraction and it would squeeze the blood out of the way, because we have a high pressure system with those contractions, and it's going to push the blood into a lower pressure system. Now, the way that this calcium gets down into the T-tubule and signals to the cell is via electrical signaling. So there's different types based on the different type of muscle or tissue that we're looking at within the heart. So we have our pacemakers, which are essentially going to initiate and propagate the signal across the heart. So we have our pacemaker cells, which will continuously depolarize very rapidly, roughly around 100 times per minute. And as this happens, we see calcium coming in to the muscle cell and potassium going out to even out the charge. As this occurs, we see a positive inflection within our electrical signal, which is going to initiate a contraction as long as it reaches its threshold. So for example, I think the threshold is around here. So as soon as it reaches this threshold, the calcium will continue to rush in and initiate this attachment here and the contraction. Once this is reached, the heart and the muscle cell wants to return back to its equilibrium. So as we go into phase 3, the calcium is exiting and the potassium is coming back in to return it to normal. Now, with these pacemaker cells, like I said earlier, it happens very quickly, so there's not much time where it'll sit at its resting potential. So we instantly go back into our depolarization. Now, within the actual muscle cells, like we see a ventricular myocyte, once the signal is received from this pacemaker cell, we will see an exchange of sodium and potassium instead, and then a little bit of calcium playing in. But we'll have sodium coming in and potassium going out to initiate that change in charge. We'll have, once it reaches its threshold and enough sodium comes in, we will see a large influx of sodium and a large efflux of calcium. Now, while we're trying to cause a lot of pressure and a lot of time for the pressure to build up, we'll see a little bit of calcium come back in, and then it'll sort of plateau in phase 2. Calcium is also entering in this time and binding at this muscle cell to help create as strong of a contraction as we can. Once the contraction has been initiated and it is in active contraction, we will see a lot of potassium come back in order to reach that threshold and equilibrium again. Here we see a little bit more of that plateau as the cell is waiting for another pacemaker signal to come in. It allows it time to reset and detach calcium from these binding sites. So the way that these signals physically go through the heart is with different nodes, is what we call them within the heart, where there's a lot of electrical activity. And the first one that we talk about in order is the SA node, which is here. It stands for the sinoatrial node because it's at the septum of the two atria. This SA node is going to receive signaling from either the SNS or the PNS, depending on what's active. Once it receives its signal, it'll send the signal down the atria. So we will see the atria contract and shrink down, squeezing blood into these ventricles here. This happens very quickly, which is why we see heartbeat like signaling go very quickly. So as the atria contracts, it's able to do so because of something called functional syncytium. So all of the cells within the atria, within the heart as a whole, but within the atria specifically right now, have intercalated discs, which basically allows each cell to be very mildly connected so signals can travel through quickly. So instead of the cells being cut off and separated here, the electrical signal can pass through these intercalated discs and travel much quicker through the heart, causing that quicker contraction. Once this signal is sent down, it collects here at the AV node. It'll slowly collect over a little bit, I say slowly, relatively slowly. It will collect at the AV node. And the reason why it collects at the AV node is because it's allowing the full proper time for these atria to contract and squeeze blood into these ventricles. So while the blood is being squeezed down and through, this AV node is collecting that signal. Once this has come to an end, the AV node is ready to send down its signal. It will send them down this septum, where we have our bundle branches, and then back up towards the center of the heart through the Purkinje fibers. And what this allows is the ventricles, if we're down here, it'll cause the septum to come up, and then it'll squeeze from the bottom up, squeezing blood out to the system or to the lungs, depending on where it's going. We allow full time for this contraction to really propagate because it is crucial that these ventricles are able to squeeze out as much blood as they possibly can in order to get the system the nutrients and blood that it needs. So I guess the next thing we'll talk about, I have a note somewhere, would be heart failure. So heart failure occurs whenever the heart is unable to pump a sufficient amount of blood, or it is unable to provide the body with whatever it needs. This can happen in multiple different ways, whether it be a failure in the muscle or a failure in the electrical system. Whatever it is, it's unable to perform its job. So there are two types of heart failure. There's HFrEF and HFpEF, and these stand for heart failure with a reduced ejection fraction and heart failure with preserved ejection fraction. Ejection fraction is essentially discussing the proportion of blood exiting to the proportion of blood entering the heart. So if we have 60, I'm not entirely sure what the actual measurements would be, but 60 milliliters of blood leaving the heart, and we have 100 coming in, our ejection fraction would be 60 over 100. Whenever the heart has this number dropping or this number increasing without sufficient change of this, we will see a reduction in this ejection fraction. So HFpEF typically comes first, and with this one we see an inability of the heart to take in blood into this right ventricle. So this can be due to essentially a lot of stress on the heart causing hypertrophy in this ventricle. So as you have hypertrophy, obviously you're adding sarcomeres, you're making these heart walls thicker. There's now less space for blood to fill in. So if these are the walls, there's less space for blood to fill in and be pumped to the system, to the lungs, wherever it needs to go. So this is what we would call a filling issue or a diastolic issue. If there's not blood entering the heart, there's not blood to be pumped out. So we have preserved ejection fraction. Our fraction of blood out to blood in is still above 50%. Now HFrEF occurs whenever we have reduced ejection fraction. So we could say that this left ventricle is not contracting in a way that it needs to in order to keep up with the needed ejection of blood from the heart. So It's a much more qualitative way of assessing everything, but basically it's interrupting the systolic function of the heart, which is basically how much blood is exiting. Whenever we see this, it's typically due to a lot of back pressure in the aorta causing increased afterload in this ventricle. Whenever we have increased afterload, we have more blood sitting in the ventricle than it can really hold. We cause the muscle to stretch. Whenever the muscle stretches, we see these actin and myosin filaments becoming farther and farther apart. Whenever they become farther and farther apart, they're not able to reach each other and contract as well. Whenever they stretch too far, we see them unable to grab and reach each other to contract. This is called the Frank-Starling mechanism. So essentially the way that the Frank-Starling mechanism works is we have, as stretch increases, you've got more room and more contractile force up to a certain point. Once it's stretched beyond what it's capable of, we see a reduction in how much contractile force it's able to produce. So here, if blood keeps filling and filling and filling, this ventricle is going to continue to stretch and stretch and stretch, and its actin and myosin filaments will not be able to reach, which would ultimately cause a break in inotropy or contraction. So, basically, we can see signs and we can see symptoms of heart failure within somebody whenever they are going about their daily life, but as far as actually diagnosing and testing for it, we'll most commonly perform what's called a nuclear stress test. With a nuclear stress test, we inject the person with radioactive glucose, and what this does is the glucose is obviously what your body uses to produce energy and perform muscular contractions. So the glucose is going to go to active muscle. As the muscle is using the glucose, it's going to use it, eat it up, and dispose of it. Whenever we have active muscle that's performing the way it needs to, we will have a normal metabolic rate or a hypermetabolic rate of that glucose, meaning that it is normally or excessively using and eating the glucose. If we have a dead area of the muscle, like we would see here, if there's a dead area, it's not going to be able to use or consume any of that glucose. So we would perform scans on the radiation to see where it's accumulating. If there's more of that radioactive glucose accumulating, we will see it highlighted within the screen, and that shows us areas in which the heart is hypometabolic, where it's not eating the glucose, meaning that that muscle tissue is dead and unable to perform the electrical signaling or the contraction that we need it to. So to kind of just go over everything as a whole, we've got our different types of contractions. We've got, well, not contractions, but electrical signaling. We've got our pacemaker cell sending signals very rapidly to the heart to propagate a signal and propagate contraction later on. Once the signal is propagated and received by the muscle cell, it'll reach its threshold, hopefully, and cause a big change in the electrical signaling of the actual muscle. And we do this via the exchange of different chemicals within the body, whether it be calcium and potassium or sodium and potassium, as we see in our muscle cells. Once these signals are received by the muscle, we will see that calcium change entering the cell, causing signaling within the cell and binding at the tropomyosin. Once the tropomyosin moves over, we'll see actin and myosin grab onto each other and sort of act as though they are grabbing onto each other and ratcheting towards each other, shrinking the cell, causing a contraction, and in a line we'd see a bigger contraction of the muscle. As we mentioned with heart failure, if the heart is stretched out, like the muscle is stretched, this contraction is not able to occur because these actin and myosin cannot reach each other. This is going to cause heart failure with reduced ejection fraction due to decreased inotropy. Back to electrical signaling. We've got our SA and our AV node. Our SA node is going to send signal down the atria, where it's going to collect at the AV node. It's going to go down the bundle branches and up the Purkinje fibers, where it's going to reach this dead layer of cells and end the signaling until the next signal is sent down, collected down the bundle branches, up the Purkinje fibers, receiving at this dead part of the cell. With our heart failure, our heart is unable to perform the way that it needs to for whatever reason, whether it be an increase in afterload causing an increase in back pressure, increasing afterload causing a stretch and break in inotropy in the left ventricle, or an overworking of this right ventricle causing hypertrophy and reduced filling space. Whenever we have that inability to perform, we can test for that with nuclear stress testing to see where radioactive glucose is metabolized and used by the heart. And we can see exactly where it's failing. I think I forgot to mention, this is a cross section of the heart, so if we were looking at the heart, we're looking at it in this Z plane. So we've got our X plane, our Y plane, and then our Z plane. We're looking at kind of like if you were to cut the top off of the heart, we'd be looking at the muscle as a whole, and we would see a septum. And we're looking at how this heart is consuming the radioactive glucose.